Hello and welcome. Today's topic is 3D modeling for 3D printing. So now we have talked a lot about the 3D printing and 3D printers and 3D printing technologies and the settings for them and stuff like that. But now we should take a look how we should do the 3D modeling. So these are the topics. There will be stages of the 3D modeling, and then the printing technologies, the shapes of the parts, inserts, threads, splitting into parts because we might have big prints, the orientation meaning of the part, and saving the files. First, the stages. We have been through this a few times. So basically this is again the part of the 3D printing process itself. There's the idea, once again. Then there's the difficulty to determining the technology that should be used. And then the requirements for the part. The requirements for the part, which also affects the technology used. So if the parts will have some kind of small details, we should think about which technology to use. And if it will be a big print, we should also think about that which technology can be used for big prints. Then the modeling itself, how the piece should be modeled. And then the saving. So, printing technologies. What it means, how it affects. So here's the printing technologies affection. If we talk about generally FDM 3D printing, for example, a part that is 1 millimeter in height, and if we use 0.15 millimeter layers, we know that it doesn't add up quite nicely. It doesn't go even because 1 divided by 0.15 is around 6.6. So it does have to compensate with one of the layers or few of the layers to get that 1 millimeter of thickness to the part. But then again, if we use 0.2 millimeter layers for that 1 millimeter, we get an even result and it adds up a bit better. So if possible, the layer thicknesses should be taken a bit into consideration when 3D modeling. You don't have to take it into consideration, but if it's possible, it should be used because it helps with the quality a bit. And same goes with the wall thicknesses. If we have a part that has a wall thickness of 1 millimeter, and usually the nozzle is 0.4 millimeters. And if we use a 0.4 millimeter nozzle on a 1 millimeter wall thickness, and we said that there will be 2 perimeters or there will be 2 perimeters for that wall. It can't go and push 2 lines of material and be happy about it. It will have to compensate again. It will have to either over extrude the material so it achieves the 0.5 millimeter for each line, or it has to create a gap between the 2 lines so it can push infill there or just keep it empty. Basically, again, if we want to optimize, we should have the wall thickness that can be divided by the nozzle size, and the result should be even. It's not mandatory, but it will bring ease to the printer and better results. I won't say that it will create a huge difference, but a tiny difference. If it's possible to use a bit bigger walls that are dividable by the nozzle size, you should do that then. And then there's the engraved details, the embossed details, and the holes. And these are a bit different things because with different technologies come different possibilities. If we talk about Sls printing and take for example, PA11 material, nylon PA11, you can have minimum of 0.4 millimeters of engraved detail. minimum of 0.4 in depth and in width. And embossed details can be, again, minimum of 0.4 millimeters in height or width. The holes, it's again around that same area, so 0.5, 0.4 millimeters. And on plastic, like FDM machines, the engraved and embossed details are 0.2 millimeters in depth and in width. And if there's like a text that is engraved or embossed, that should be 0.5 millimeters because it won't be readable. Holes, again, it really depends on the nozzle size that you use. Even holes that are 0.2 millimeters can be achieved, but they can be a bit tricky. Well, with printing metals, for example steel, the engraved details can be 1 millimeter in depth and width, and embossed details also 1 millimeter in height and width. Holes are pretty much the same. This again depends on the printer used for the printing metals. I mean steel. For aluminium, 0.4 or 0.5 millimeters for the engraved or embossed details. If it's just a little detail, but if it's like text that you want it to be readable, then it should be around 1 millimeter in depth and width and height when talking about engraved details and embossed details. Pretty much same goes for the holes. So it depends on the technology used that how accurate details you can achieve. So what about escape holes or clearance? Because some 3D printing technologies require escape holes. For example, SLS. If you create a part that should be full, but you want a cavity inside, or like you want it to be a shell, you need to create an escape hole for the powder to get out, so you can push it out from the print when it's finished. And the wall thickness also, these are again depending on the technology. For PA11, for example, the SLS technology, the escape hole should be around 4 millimeters, and minimum wall thickness is 0.4 millimeters to 0.5 millimeters. Same is for plastic, so clearance, wall thickness around 0.6 millimeters. Because if it's exact width of the nozzle, if it's the same width that the nozzle is in diameter, you will have a very, very flimsy wall, and it won't hold. It will break very easily. When talking about printing metals, escape holes, again, because if using metal powder, for example steel powder, 4 millimeters and 2 millimeters around should be adjusted for the escape holes. And clearance between parts should be 2 millimeters. So if you print a full print bed of parts, they should have clearance of 2 millimeters from each other. And wall thickness for these metal parts should be 1 millimeter minimum. And when talking about printing aluminum, escape holes should be 4 millimeters. And if there's several escape holes, then it should be around 2 millimeters. Clearance, again, 2 to 4 millimeters in between each part. And the wall thicknesses for the aluminum parts should be 1 millimeter. What about then the shrinking and details? Well, when talking about SLS, it doesn't shrink, so it doesn't affect that or do any deformations, but the details that can be achieved is like plus minus 0.3 millimeters. For example, if like the spikes shown in the image, they don't come out as very pointy spikes. They come out as dull spikes, but if it works, If it works that way, then it's good. And with plastic, the details again can be around 0.3 to 0.7 millimeters. That's the detail level that can be achieved. And again, with plastic, you can get a pointish tip, but again, it will look a bit more like the one on the right that is circled. And when talking about steel, that's a material when it's done with powder bed fusion, so DMLS, it can shrink plus minus 5% and more on the smaller holes or inner diameters for parts. With aluminium, it's shrinkage of plus minus 0.2 millimeters when the product is under 10 millimeters. If the product or the object is over 10 millimeters, then it can shrink or deform in each direction plus minus 1.5%. So also in the right image, you can see a picture how the cone will be shaped with an FDM machine. So at least the 2 or 3 top layers won't hold on or come out nicely in this example. So what about the need of supports? When using SLS machines technology, you don't need any supports because the powder itself will act as a support. When using plastic, you will need supports, but you can also use support materials which can be dissolved in water or chemicals. And when using with SLA or MSLA technology, you will need also supports. When printing with steel or aluminium, again, you will need supports. What about the shapes when talking about 3D modeling? Modeling shapes that support so that supports won't be needed. So if we make like a pillar that has like these little bridges that will start on going outwards of the piece, if we use a fillet or a chamfer for that, it will come out nicely and it won't need any supports to get that printed. If the part or the thing that comes outward from the piece is straight up in 90 degrees and there's nothing underneath, that won't come out without supports. That will fail. Or the downside of the print will be really, really ugly. And these are examples when talking about FDM 3D printing. What about holes in horizontal direction? If we make circular holes, it won't be like 100% round. If we make a bit hexagon shape, which can then be drilled, of course the round hole can also be drilled to the right shape. But if we use like that hexagon in the middle, can be printed without supports because there's pretty much nothing that will be completely in air because there's the angles going to the middle. So it supports itself. And on the right, there's the teardrop shape, which helps out so it won't need any support because the on top of the circle won't be laying in thin air because the sides are supporting it from the side, so it will help out. And the shapes, again, whether use fillets or chamfers. Fillets can be used mostly on the top side because it's a round shape and the print consists of layers. It would have to be like really, really small layers so that the fillet could come out nicely in the print. And using fillets on the top side, it works again because it will have some surface where it can be laid on. But if you use chamfers, that's good because it will be an angle and that's possible to print without supports. So what about inserts? What about those? What does this mean? That can you push something inside the print? Can you adjust the print with an insert? In the top left image, there's a test of using this fabric, and after printing a layer or two, there was first printing a layer to 2, then adding this fabric there, and then continuing the print. You could create this fabric with these claw, these needle types on that. So you can create basically accessories to your clothes with this type of technology. And on the right, there's an robotic gripper that you could use the inserts in the middle of print or post print. You could use a little hex nut there that can be then tightened to the other part. So this offers flexibility on different types of surfaces that can be used, or textures, adding nuts, bearings, wires, so electronics can be used there, or like carbon fibers on LEDs or anything. You just have to take that into consideration in your print. Even copper wire can be inserted into the print, as you can see in the image on the middle. There's copper wire coming with the melted plastic. And this can be really done in the middle of the print or post-print. What about threads? So threads, thread inserts, or nuts, or nut-shaped. So how you should do it? Should you use thread inserts, or should you use nuts that you push into holes that are shaped like a nut, or slots? There's different possibilities to use this. Designing a nut-shaped hole might be really the easiest one, and it's really quite durable in the end. Or do you model the threads into the prints? Or do you use inserts that you melt then again to the print? First you design a hole and then push the insert there. Or do you make these threads yourself for the parts? Or how do you design it? It's all affected by the technology again, and the durability of the part. Basically, 3D printed threads work, but if it's possible to add nuts or thread inserts, you should use those. So splitting the object into multiple parts, again, something that might be important. So this again, affected by the technology used. The parts on the below or the right hand side can be done, for example, with an Sls machine without the need of supports or splitting it into parts. But if we use, for example, FDM technology, it should be split into several parts. Or yeah, you should split your part into several parts if it's a difficult shape, like the one in the one in the below. You will create because if you split it into different parts and then just assemble it, you will get more accuracy and more details. It will become a nicer looking part. And if you have several printers, obviously this will be then a lot faster to print. And you can make different materials, of course, in the same print if you split it into parts. And on the right hand side, you see a robotic vacuum gripper that was printed in 3 parts. Because it made more sense to use it like this, because then it enabled a thing called modularity. So we can now change the amount of vacuums used in the gripper, or we can adjust the distance between the 2 vacuums by changing the head of the vacuum gripper. There's few ways how you can obviously split it into multiple parts. When you start the designing in that aspect that you will create it in several parts, then you just model different parts and make them work in the 3D model and then print them out separately, like the 3 examples on the top. Or if you have already designed the part but it's just big, you can use different softwares to cut it down into pieces. For example, on the left there's a human head that was then cut into pieces using a software called Blueban. And in the middle, the same thing. There was a part that was cut into shapes of different sizes with the software called Blueban, and it does this automatically. Or like in the image right hand side, you can cut the part into different sizes in the 3D modeling software. So basically the best way is to obviously design the part to be printed in several different parts, because that enables you to use different materials, or it gives you the freedom to test out different things, and it gives you the freedom that if the part doesn't fit, you don't have to print every part. I mean, you don't have to print the whole thing again. You can just print one of the things. So orientation. Orientation obviously affects the part's durability. There's the interlayer bond strength. So there's on the image above, you can see the same part printed in two different orientations. There's the thicker wall, and then there's the thinner wall. And if the idea for this part is to act as a support, we can right away see that the part on the right hand side will snap at the root of the connection of the thicker part and the thinner part, because the thinner part will be having a serious durability problem on that thinner part because it's printed in that direction. It affects the strength of the part. It doesn't hold up much in that direction. But if we turn it 90 degrees to the right, like in the left image, the left part on the image, it will have considerably more strength. It can withhold more pressure pushing that thinner wall. So what about the strength of the 3D printed parts? You can see a chart on below that tells us the tensile strength of ABS plastic when it's infilled 100%. There's different manufacturers and different lines. And we had these tests pulling these dog bones that are used in the ISO 527 standard, the standard test, tensile strength tests. And we could see that when the prints were printed like shown in the image on the right, the strengths were close to 1000 to 2000 newtons, the tensile strengths. But if we printed them like in the position shown on the left image, the upward position, we could see that the weakest link wasn't the material itself, but it was their internal bonding. So the plastic didn't bond so well. So it snapped quite easily. You could easily snap these parts with your hands, and the parts that were printed like in the image shown on the right, in that direction, you couldn't break them in half with your bare hands if the infill was 100%. So it affects the strength of the part considerably. Let's say that. So what about the last thing, the saving? Well, there's different file formats that you should use. There's STL, OBJ, AMF, 3MF, there's PLI or VRML. These all depend on what 3D printing technology you use, because not every technology accepts every file. But if we're talking about FDM technology, STL is the great way to go. The STL is the one that works. And there's a new format called 3MF, which is a new one, which also works quite well. But STL is basically the one that is the most common one used when 3D printing. So what are the supported file formats for different slicers? Well, as you can see in this image, STL is in each slicer software. In Formlabs, in Cura, in Slick 3R, in Repetier, or in Simplified 3D. And Prusa Slicer also supports STL, OBJ, and 3MF. So that was a glance to the 3D modeling for 3D printing. Hope you enjoyed it. See you in the next one.